Good afternoon, and welcome to an exciting event, an exciting afternoon in which we'll start talking about green chemistry and toxicology and how they interconnect with each other and lead to a better education for chemists and for green chemists. This is Darila Kovac from Grand Valley State University and one of your hosts for the seminar today. And I want to remind you that our seminar entitled The Need for Toxicology in Chemistry Education, the Making of a Green Chemist, is actually hosted by Grand Valley State University and Michigan Green Chemistry Clearinghouse. Our webinar today is actually, can you change the slide, Clinton? So the seminar today and the need for this complex title came from the idea that green chemistry education is going forward, but toxicology connected with this is lagging behind. So this webinar is intended to be the first in a series which is looking to promote toxicology as a needed learning objectives for chemists, and we would like obviously to take the green from green chemists and say that it's going to be for all chemists. But right now we are going to focusing on the need of toxicology in teaching green chemistry and proficiency in green chemistry. And we would like to initiate a conversation about toxicology among chemist educators, health professional, industry, and the broader public. Can you, next slide please. We are bringing together the 3 different specialists in toxicology with different background, and we hope to be able to integrate their perspectives to raise awareness about toxicology and mostly to generate ideas for incorporating toxicology into chemistry education. Our ultimate goal, and we hope that this project is going to be able to lead to the fruitful objective that we have in mind, is to develop learning modules for teaching toxicology to chemistry and to chemistry students and to anybody else interested in green chemistry. And we hope to have these toxicology modules available for everybody, both on the Michigan Clearinghouse and also Green Chemistry Clearinghouse and also at Grand Valley, having in mind to offer those modules to people which are taking the green chemistry certification. As you can see, our invited speaker today come from different background with different and are going to present different topics connected with toxicology. So I'm excited to introduce our first speaker today, Richard Radesky, which is a professor at Water Resources at the Annis Water Research Institute. He has a PhD in Environmental Health Sciences from the University of Michigan and 18 years of research experience in environmental toxicology. Rick is going to give us a brief introduction into toxicology principle and practice and also talk a little bit about environmental toxicology. The floor is yours. Thank you, Rick.
Okay, I appreciate the opportunity to give an introduction to the field of toxicology. And toxicology first started when people were trying to figure out what was poisonous in terms of what kind of plants to eat, what kind of plants not to eat, how much medicine to give to somebody, and then it was also used for nefarious purposes in terms of poisoning for political advantage or whatever. Since then, it's changed into a very diverse science that deals with the adverse effect of chemicals on living organisms, so it's expanded from humans to all organisms, and then to assess the probability of their occurrence, the adverse effects, so it's gotten into a preventative mode also. Next. Next slide. Okay. Just an outline of the presentation. We're going to talk about some of the history of toxicology, get into the foundation of toxicology, which is dose and response, some information on types of toxicants, and then the potency, how strong a chemical is as far as toxicity, And then just a little bit on the complexities of environmental toxicology, applying toxicology to the environmental setting. Next. From a historical perspective, I like to start out with this statement, and it says the appearance of diseases in human populations is influenced by the quality of air, water, and the food, the topography of the land, and the general living habits. And most people think that statement was made in the 60s or 70s, 80s. It's a very holistic type statement. Next slide, or next. But it was actually said back in 400 BC by Hippocrates, the famous Greek physician. So we had an understanding of the holistic nature of our environment, the quality of food and water, lifestyles, and landscape issues. It's just, I need to remind people that it's not a new concept. I mean, we had that understanding a long time ago. Next. Toxicology was, the principle of toxicology was first stated by Paracelsus back in the 1400s, early 1500s, and he's considered the father of toxicology, and his famous statement was, all substances are poisons. There is none that is not a poison. The right dose differentiates a poison from a remedy. So he was the first person to associate poisoning with dose. So all chemicals have a dose. Some is greater and some are less that can cause a problem and act as a poison. Next. Then in 1815, the Spanish physician Ophelia established toxicology as a scientific discipline. So its first origin was in the medical profession, as established in the field of medicine. Next, please. Today we have a very diverse science, and I just wanted to introduce some of the different types of toxicology that you can choose to study or practice. The first is mechanistic toxicology, and that's the study of how chemicals cause toxic effects with respect to absorption, distribution, excretion, cellular levels, molecular levels. So just looking at the aspect of toxicity from a mechanistic standpoint. The second form is descriptive toxicology, and these are individuals that run bioassays, so they're actually looking at certain endpoints and doing experiments with different types of living organisms. And then in the medical sense, we have clinical toxicology, and these are individuals that are studying the effects of drugs and chemicals on the body, looking at treatment and prevention, but it's primarily done in the pharmaceutical settings. Next, please. Then we can move into forensic toxicology, and this is made popular by the TV show CSI, and this is a branch of medicine that looks at the medical aspects of poisoning. So we're trying to find out what caused a human death when poisoning is involved. It also involves analytical chemistry to look at the toxicants. And then environmental toxicology, that's the area that I work in, and this is the study of pollutants on organisms, populations, ecosystems, and the biosphere. So again, we can look at very small, something like bacteria, and then move into whole ecosystems, and then the whole world. Finally, we have regulatory toxicology, and this is where we try and take scientific data, and we look at how to protect the health of humans and animals from excessive risk from chemical exposure. And we primarily look at this as something in the public sector, regulatory agencies, but a number of companies actually have toxicologists that work in getting permits or getting certain chemicals able to go out into the marketplace. So we see that both in the public and private sector. Next, please. So I want to go back and look at the dose-response concept and just take a look at dose first, and that's the amount of chemical entering the body, and it's usually expressed in terms of milligrams per kilogram body weight. So it's always on a milligram per kilogram body weight expression because obviously it takes more of a tranquilizer to affect an elephant than to affect a dog. So and in terms of humans, we typically dose like baby aspirin, different levels to than an adult. So we always look at it in terms of the body weight of the organism we're looking at. And then the dose depends on the concentration of the agent that you're giving. So sometimes you're taking a pill that's got a pure compound in it. a certain weight, or other times you're inhaling air with a certain concentration of a chemical. So the concentration is important. The properties of the toxicant are important, if it's water-soluble in your bloodstream, or if it's exhaled, or if it's lipid-soluble. Those kinds of issues come into play. The timing and frequency of the exposure is important in terms of how much a chemical is, how often you're exposed, and then whether you're exposed at an early time in your lifetime or later time. Exposure pathway is important, air, water, and then the length of exposure. Are you exposed for a couple days or for a longer period? Next, please. And then the response is also important, and that's a change from the normal state. It could be a cellular, molecular, organismal event, local or systemic actions, irreversible or reversible, immediate or delayed. So you can see that the response is also fairly complex. Next, please. And then in terms of toxicity, we have two ways of classifying toxicity. One is acute, and that usually involves lethal concentrations, short-term exposure. We're looking at death. And then we express that as an LD50, lethal dose 50, that's the level of a chemical that kills half of the population. And we get that by plotting what we call a dose response curve. So it's over a population looking at multiple doses. Next. And I have a dose response curve on this slide, and you can see that between 5 and 10 is the lowest concentration, and then we go all the way up to a little over 30, and then the level that causes 50% death in the population is right at 20. So we can run experiments and then plot the curve and then get the LD50 from the curve. Next. And then we can look at chronic toxicity also, and that's a longer-term sublethal exposure. So we call that endpoint the ED50, or effective dose 50. And this is the dose that half the population is affected by a particular chemical. So our effect is anything but death. It could be lethargy. It could be dizziness, just any type of a endpoint. And we do the same thing. We plot the concentrations and look at the population response with respect to dose. Next. And you can see here a ED50, or a chronic toxicity dose response curve. It looks really similar, only our endpoint is different. But I want you to look at two areas on the curve that are very important. First is the lower concentrations. You can see a threshold. And the lowest concentration that produces no effect is called the NOAEL, or no observable effect concentration or level. And then the concentration where we see an effect for the first time is called the LOAEL, or lowest observable adverse effect level. So that's the concentration where an effect is observed. So by plotting that data, you can see the ED50, the concentration where 50% is affected, but then two other really important parts, the no effect level and then the lowest level where we see an effect. Next. And then we can look at the dose response curve for multiple chemicals, and by plotting them on the same graph, we can see that certain chemicals are more potent or cause an effect at a higher or lower concentration. And you can see the highest potency has the effect at the lowest concentration on the far left, and then moving to the right, we have a low potency compound, and you can see that the 50% dose is about 10 milligrams per kilogram for the low potency, and for the high potency it's less than, well, it's about 0.1. So that's how we judge potency, by looking at the dose response curve. Next. And then I wanted to talk a little bit about some of the other types of chemicals. And we have chemicals that cause cancer, and those have really no threshold, because in a sense one molecule could cause cancer. We generally look at those with respect to risk. Generally a 1 in a million risk is considered acceptable. And we have to extrapolate that level, because about the most sensitive measurements we can make with bioassays is about 1 in 100 in terms of cancer in laboratory animals. So we have to model that difference from what we can measure to what we want as an acceptable risk. And then finally, we have something called hormesis, and that's a biphasic dose-response curve. And I've got examples on the next slide, but this is indicative of a chemical that has a beneficial concentration at low dose. And then in the absence, you have adverse effects. If you have a low dose, you have stimulation or beneficial effects, and then at high dose, you have inhibition. And next slide, please. And I've got all three types plotted on this graph here, and you can see that a threshold toxicant essentially goes through zero and it's a linear line. And then we have the hormetic curve next, where we see that in the absence of the chemical, there is an adverse effect, but then as we increase the dosage, there's no effect. The action of the organism is actually healthy. And then as we increase the concentration, there's an adverse effect. So example of that would be something like vitamin D or selenium, something that's a trace element or a vitamin, and it becomes toxic at higher concentrations. Some toxicants like ionizing radiation also have a hormetic curve, so that further complicates the study. And then finally, our standard dose-response curve furthest to the right that has a threshold and then a toxicity response. So these are the types of dose-response curves we have. Next. And then finally, toxicity varies over populations. And we have a standard bell-shaped curve where we have sensitive populations that respond to lower doses. In the middle, we have the average population, and then we have insensitive subjects or insensitive populations at the far end. So why don't you advance 2 times? And babies, infants, and the fetus turn out to be very sensitive populations. Also, people with compromised immune systems, elderly people. So these are all populations that are sensitive. And then 2 more times, advance. On the far end, we have Keith Richards and Ozzy Osbourne, very insensitive to chemicals. So they represent insensitive populations. Next. And then within these groups of chemicals, we have toxins that are, and these refer to biological compounds. A lot of times, toxic chemicals and toxins are used interchangeably, but toxins only refer to biological compounds, and these are things like ricin and botulism. We have carcinogens, and these cause cancer, increases in tumors. Benzene, benzoate, pyrene, vinyl chloride are examples. We have mutagens that cause hereditary effects, and these affect germ cells. Radiation, nitrosamines are examples. Teratogens, and these are chemicals that cause impacts to the offspring. German measles, rubella is an example. Thalidomide, PCBs, anything that affects the offspring or growing fetus. And then finally, endocrine disruptors, and these are chemicals that mimic hormones. PCBs, PBDE, DDT are examples. Next. And I'd like to use ethanol kind of as a study case, so next, please. And starting out with a little cartoon, we say that, drinking kills brain cells. What are you going to do after you've killed your brain cells? I'm going to go into politics. We kind of make a joke out of alcohol exposure, so it's an example that our perceptions are often associated with the degree of pleasure or displeasure with an associated risk. Next. And I just wanted to show alcohol related to other chemicals, and alcohol has a toxicity of 10,000 milligrams per kilogram. It's one of the least toxic chemicals out there. Compare that to nicotine, which is 1 milligram per kilogram. So it's really on the toxicity spectrum very less. Next, please. What type of toxic chemical is alcohol? Next. It's a group 1 known human carcinogen, so it's known to cause cancer. It exhibits hormesis in terms of small amounts being beneficial. Next. It's a teratogen because of fetal alcohol syndrome. Next. And you can see that from the Institute of Medicine's report to Congress, it's a very serious problem in terms of effects on the fetus. Next. And alcohol is a very potent teratogen because it diffuses right across the placenta. That's usually a barrier. The concentration in the fetal blood is the same as the mother's within a few minutes, but the fetus cannot metabolize it. It only metabolizes 10% as fast as the mother, and up to 1 in 200 worldwide are affected by prenatal alcohol exposure. Next. And you can see from this figure that how sensitive the fetus is, because the fetus is undergoing central nervous system development somewhere between 3 to 5 weeks with respect to the pregnancy. So any alcohol exposure at that time, and this is kind of background to why the timing and sensitive populations are so critical with respect to toxicology. Next, please. Finally, endocrine disruptors, and these are compounds that mimic hormones. So they can mimic the hormone, have the same effect. They can block the hormone, or they can stimulate or inhibit endocrine systems. So they interact in several different ways. Next, please. And this is just a little depiction of how this receptor and endocrine disruptor interacts. And you can see from the top picture that you're looking for a particular structure. The receptor is looking for a certain structure that the hormone provides, and that initiates a response. The bottom picture shows a hormone mimic having some similar structure to the original hormone, and it can either cause a response, as it shows in this picture, or it can disrupt it, or it can trigger, something different. So it can stop the response, or it can trigger a different response. So it's a structure and function type of relationship. Next. And I just wanted to show some examples of endocrine disrupting compounds or hormonally active compounds. You can see estrogen at the top, and these are all compounds below it that are called endocrine disruptors, or they act to mimic estrogen in biological systems. And if you look at the far right-hand slide, you can see it's this terminal phenyl group or phenol group with the OH and the aromatic ring. And all of these compounds have that. And there's also some weak estrogen activity if you put a chlorine there instead of the OH. So receptors that are looking for that OH aromatic ring function will potentially react to a different compound. Next. And again, coming back to potency, estradiol has a potency of 1. It's the strongest estrogen-type compound. Diethylstilbestrol, 0.64. Coumestrol, which is a phytoestrogen, something in soybeans. And then you can see some of the compounds that are in the news, nonylphenol and bisphenol A. They have the estrogen activity, but bisphenol A is only about 15,000 times less potent than estrogen itself. So there's a wide variation in terms of potency. Next, please. And the reason why you've got this difference in potency is it's really a three-dimensional function. If you look at the picture on the right side, you can see estrogen fitting in 3 dimensions on all the folds of the protein. It's a, you have to remember we're dealing in 3 dimensions, not that little 2-dimensional figure that I showed. And estrogen reacts because, as you see on the left-hand side, it's got kind of a bend to it. It's not a planar molecule. It's got some 3-dimensional character. BPA is pretty much a flat material, so it doesn't necessarily fit in that receptor very well. That's why it's very ineffective as an estrogen, environmental estrogen. And then we have MBPA, or MVP, which is a metabolite of BPA that fits in much better, but that's even 100 times less than estrogen. So again, potency is really important to consider. Next, please. And then I just want to say a little about environmental toxicology. And if you look at all the disciplines that go into environmental toxicology, you can see it's pretty diverse. Everything from molecular genetics to chemistry to ecology, landscape, meteorology, geology. So it's a very diverse science and requires experts in all those fields. Next, please. And then when you look at dose in terms of environmental toxicology, it's not as simple as taking a pill or a workplace exposure. You're exposed at home, you're exposed at work, agriculture, soils. You're exposed from consumption of food products from animals, drinking water, and you're not only exposed, but you also have the potential to expose the fetus in the womb. So it starts out as a chemical from industry or a chemical from a personal product or something like that, and then it gets spread out over a variety of exposure routes to finally looking at the human. So it's very, very complex to try and model that or understand that. Next, please. And then to summarize, toxicology is a very complex science, but it's founded on the dose-response principle. And the environmental exposure really adds complexity to that. And human perception is important because we consider alcohol to be, relatively safe, yet it's just as toxic as a lot of the other chemicals that we're very concerned about. And then finally, green chemistry is very important to provide solutions to coming up with chemicals that don't have this type of an issue with respect to toxicity and human exposure. So I'll end with that.
Thank you very much, Rick. We really appreciate for bringing us up to speed. There is a lot to learn from only become familiar with the terms. So I want to encourage the audience at this point to start typing the questions in. So if they don't forget what they would like to ask you, because I'm going to collect the questions and bring them up in the question and answers session at the end. Thank you very much again, Rick, and I'm going to move now to our second speaker, Carol Henry, which is a professional lecturer at George Washington University School of Public Health and Health Services and a consultant to SAE International. She advises organizations on issues in toxicology, risk assessment, public and environmental health, sustainable green chemistry, and engineering practice. Dr. Henry received her undergraduate degree in chemistry from the University of Minnesota and a doctorate in microbiology from the University of Pittsburgh. She is also a member of the Joint Committee on the ANSI-NSF Green Chemistry Institute Green Chemical Products and Process Standards Initiative. And I can speak more about Carol's credentials, but I would let her talk for herself. And thank you very much, Carol. The phone is yours.
Thank you very much, Tallulah, and thank you to the organizers for asking me. I hope I can be heard at this time. So I thought I would take a little let's go to the next slide, to really talk a little bit about the threats to public health and the environment and perhaps how we got where we are today. Some of the laws and regulations that have been put in place with regard to trying to prevent pollution. The risk assessment paradigm, which is really comes from the whole framework for regulations. A little bit more on the science of toxicology. The revolution in biology and technology that is driving changes in toxicology as well as in risk assessment. And then green chemistry and engineering is how it might fit into some of the solutions, as Rick just said, and then an outlook for the future. So if we go on to the next slide. I wanted to sort of put a framework here. There have been some tremendous public health achievements in the 1900s. They aren't always the things you might think about, but from vaccination to safer workplaces, healthier mothers and babies, family planning, fluoridation of drinking water, and recognition of tobacco use as a health hazard, all of these, and perhaps the control of infectious disease, all of these have led to an increased quality of life and an increased lifespan. But while the focus was on some of these disease issues that were solved, we had in the 1900s an explosion in the use of chemicals and actually environmental pollution. We'll go to the next slide. And certainly one of the hallmarks of this was when Rachel Carson published her Silent Spring in 1962. She was a marine biologist with the U.S. Fish and Wildlife Service, and she had written a beautiful book called The Sea Around Us in 1951, which got her started in sort of looking around at the environment. And she became alarmed at the widespread use of DDT and other long-lasting poisons used for agricultural control. And when she raised this issue in Silent Spring, she was actually attacked by the chemical industry for her views that they characterized it as she wanted to turn the world over to insects, whereas her point was that she thought that there was a poisoning of the earth with chemicals. This really is some of the first very great tension between environment and chemicals that occurred. While DDT had been first synthesized in 1874, its insecticidal properties were not discovered until 1939, which is when it really started to be used. And after this controversy set up with Rachel Carson, President Kennedy set up a science advisory committee, and that advisory committee really validated her thesis. So her book and her drive helped to make ecology one of the great popular causes of our time, and I believe it has really led to the environmental legislation that then occurred. There were, if we go to the next slide, there were other incidents in the mid-1900s. This is the Cayuga River in Ohio, which periodically burst into flame from the chemicals that were floating on the river. Interestingly, people were upset about the fire because it would generally burn the bridges. The idea of having chemicals and things on the river meant that there was work, that the factories were humming, and that this was a good thing. So it took a while to realize this is not such a good thing. If we go on to the next slide, the organic chemical production really rose dramatically from the early 1900s to the 1990s. After World War II, it really exploded. As you can see, the chart on your left starts in the 1920s, and by 1980, it's really gone up exponentially. And through the 90s, it has continued. So if we go on to the next one. And the result of these issues, we're realizing that the air pollution, water pollution, soil pollution was really extensive, gave rise to a remarkable series of environmental laws in the United States. All of these were passed in the 70s. It's a little hard to consider that this could ever be done again. So we have the Occupational Safety and Health Act, the Clean Air Act, the Clean Water Act, the Federal Insecticide Fungicide. Are we okay? I hope. Somebody just beeped. The Federal Insecticide Fungicide Rodenticide, Safe Drinking Water, Resource Conservation and Recovery, the Toxic Substances Control Act, Superfund, and the Superfund Amendments Reauthorization. Of interest is that while the leadership for this legislation was often driven by Congress, it was Presidents Nixon, Ford, and Reagan that signed these into laws, with the exception of the Clean Water Act, which it was at first vetoed and then overturned. So EPA and OSHA were also created during these times. So this is a remarkable accomplishment. So let's go to the next slide, because the question then rose, all right, we have this environmental legislation. What does it mean, and how are we going to regulate? And that gave rise in the 1980s to the National Research Council's document called Risk Assessment Managing the Process in the Federal Government, where the regulatory actions with regard to these environmental laws, regulatory actions in the health and environmental arena are based on two distinct elements: risk assessment, the characterization of potential adverse health effects on human exposures to environmental hazards, and risk management, the process of weighing policy alternatives and selecting the most appropriate regulatory action. Next slide. The Academy publication came up with what you may have heard about already, called the risk assessment paradigm, which is really divided into the research aspects, risk assessment, risk management. The research is really where you find the laboratory and field observations, information on extrapolation methods, their field measurements. In the risk assessment, we have toxicity assessment, hazard identification, and dose response assessment, which you just heard a lot about from Rick, as well as an exposure assessment, which is integrated into a risk characterization. That risk characterization is then sent into a risk management process where options are developed, the evaluation of public health, the economic, social, political consequences of options are evaluated, and decisions are made. I should point out that for the Clean Air Act, the issue of cost could not be considered for many of the regulations in the Clean Air Act. So health was the driver in the Clean Air Act. So if we go to the next one, the question is, okay, we've got a risk assessment paradigm, but risk of what? The obvious risks are death, cancer, acid burn, birth defect, asthma, catastrophic explosions. But there are also subtle risks, decrease in learning and memory, as one has observed from exposures to children from lead, or sensitivity of the individual, as Rick nicely pointed out in his slide. So there's a variety of endpoints that have to be looked at as one tries to perform a risk assessment. And a question, if we go to the next slide, yep, thank you. Why is risk assessment really necessary? Well, all agents can, under some circumstances and conditions, be hazardous to health. The critical distinctions among environmental agents are not their hazards, but rather the risks they pose. So the risk is a probability that a hazard, that is chemical toxicity, will be expressed under specified conditions, and risk assessment is the means and the only means by which risks of different agents can be distinguished. Next slide. So our historical, if you hit it again, our historical focus has really been on source reduction. If we say that risk is a function of hazard and exposure, most of the regulations we're talking about are, and the risk management decisions have been to control and reduce exposures and to, for source reduction. So this has said that there hasn't been quite the focus on hazard, although in the toxicity arena, which is how you determine the hazard, there have been many, many pressures. Let's go to the next slide. For toxicity testing, large numbers, there's so many chemicals, existing chemicals, many of which lack basic toxicity data. In order to test large numbers of new chemicals and novel materials, for example, nanomaterials, there are many chemicals continuing to be introduced into commerce each year. And in order to evaluate the potential adverse effects with respect to all critical endpoints and life stages is quite a challenge, both for the obvious endpoints, as we talked about, as well as subtle. And to evaluate the potential toxicity in the most vulnerable members of the population is, we don't have those tools as yet. We can try to do something. I like the way Rick had separated out the sensitive and the insensitive populations, but it's pretty tough to do in the laboratory or in epidemiology studies. And then there's a real societal drive to minimize animal use. So if we go to the next slide, these pressures on toxicity testing resulted in the National Research Council doing a study called Toxicity Testing in the 21st Century, a Vision and a Strategy. And I have borrowed some slides from that document to kind of point out what some of the challenges are for toxicology. Let's go to the next slide. I think you have to hit it a couple times. We look at biological inputs that will lead to normal biological function. If you hit it again, Clinton. We have talked about the exposure, which would get to a tissue dose, which would cause a biological interaction and a perturbation, which can impact that biological input. Next, hit it again. So there are adaptive stress responses to such things, and there may be some early cellular changes. Hit it again. And then, if it continues, there can be cell injury, which leads to morbidity and mortality. But hit one more time. Oh, back, please, sorry. One of the points here is that this new paradigm, which with the understanding of the adaptive stress and that the doses actually matter and that there is a normal biologic function, has led to trying to understand the activation of toxicity pathways to understand what the normal biology is and how that biology may be changing. While that may seem obvious now, it has not necessarily been part of the science of toxicology, but it is rapidly changing. So now if we go to the next slide, the question is, where is all this going? And if we go to the next slide, we can look at some of the things that are being done now and being considered for the future are something called high throughput screens, where there will be many in vitro studies using a variety of tissues, including humans. And if you look at this slide, you can see that if you want to try and understand how many studies you could do. When we look at humans, we can do some observational studies, but you can only do not too many of those. An epidemiology study takes a long time, and I'm not suggesting we're exposing people. I'm just using the human as a surrogate for an epidemiology study to study what humans have been exposed to. So if you do an animal study, either rats or mice or rodents of some kind, you can perhaps do 10 a year. And if you move up the chart, you can see how many chemicals you might be able to test if you move from worms up to actual cellular interactions where you could do 100,000 chemicals a day. So that's what's called a high-throughput molecular mechanism, and as the molecular biology revolution has occurred, these techniques have been incorporated. The big challenge yet is to be able to use the in vitro data and be able to relate and validate it, that it actually represents an adverse effect in humans. In some cases this has happened, and in other cases it's still a work in progress. And as you can see, the immediate human relevance, the epidemiology studies on the left are of immediate human relevance and maybe some of the things you read about in the paper every day, whereas the high-throughput molecular mechanism is not as relevant yet because we just haven't been able to get as much biology done. If we go to the next slide, one of the big challenges in biology is really trying to predict human toxicity. And I borrowed this slide from Bob Kavlock from EPA, where they're really trying to take exposure models, understand and model the tissue dose, look at molecular pathways. I think if you hit the slide again, you can see that these may become quite complicated depending on what model organisms, what model pathways, and what toxicity one can observe. These are being automated. EPA has something called the ToxCast project, where they are going very deliberately on these toxicity pathways, looking at what chemicals might alter them, so that we're learning more about the normal pathways as well as what chemicals might perturb these pathways. But this is the grand challenge, to try and predict human toxicity and before exposures have occurred. If we go on to the next one. And I think that part of the challenge here is that it's going to take a while for us to be able to do that, and in the meantime, we really should consider alternatives to try and reduce hazards, and that's where green chemistry can come in and play a very important role. Green chemistry is the design of chemical products or processes to reduce or eliminate the use or generation of hazardous substances. And I really think this is something important for all chemists to consider. It is not necessarily being done in all chemistry curricula. So that the new focus is really on hazard and how can we reduce the hazard. If you reduce the hazard, then the risk doesn't, the exposure is less important, not that it's not important, but it's less important. And we might make some very big progress for some of the new chemicals that are scheduled to be implemented. Go on to the next slide. The next slide, Clinton. So as an example of something that has been attempted, this is a standard that was put together by a group of volunteers from a wide variety of disciplines and backgrounds through NSF International, called the Greener Chemical and Product Information Standard, and this is just the chemical characteristics portion. The purpose of this was to try and bring all of the information about chemicals together in an orderly fashion. You heard Rick and you've heard a little bit from me about the differences in toxicity, the different endpoints, the different chemical characteristics in terms of flammability or ecological effects, and there has not always been a way to put this together in an orderly fashion. The purpose of this was to provide such an information standard for companies to use so that they could see where there might be data gaps, they could better appreciate the hazard so that they could decide whether they wanted to use a particular chemical or not. I think this is a start. We're going to need to do more things like this in the future. but if anybody's interested in this, we can talk about this some more. So in my few closing slides, let's go on to the next slide, Clinton. The American Chemical Society's Green Chemistry Institute has been a leader in the field in trying to make green chemistry an integral part of the chemistry curriculum. And they've put out, this is called Sustainable Chemistry in Sync with Nature. You know, there are green chemistry principles, but they've reduced those so that we could actually get them all on a slide, really saying that such principles are smarter, safer, more efficient, saves money, conserves energy, prevents pollution, designed for reuse, and polishes chemistry's public image. I think the issue here is that for the chemists who are synthesizing new molecules, for the chemists in charge of chemical processes, by thinking in terms of green chemistry, you might make different choices when you are in the laboratory starting out on some new products. And it would be really good if we thought about that before the chemicals ended up in the marketplace. So we go on to the next slide. The issue that I have is that if one looks at the guidelines that ACS puts out for the bachelor's degree program, the latest review of the guidelines have been put out this year, or end of last year, and they establish minimum requirements for the certification of a major, and the new ones have 5 chemistry subdisciplines: analytic, biochemical, inorganic, organic, and physical chemistry, where student skills have to also include communication, teamwork, professional ethics, safety, utilization of information resources. Including safety in this curriculum is an excellent step forward, but it would be also good if there were something on the impacts of chemicals on health and the environment so that chemists were more aware of what the needs are. So if we go on to the last slide, I think that the whole issue of sustainability is really challenging the chemical enterprise, and that we really need to band together to see how to address this. I think that green chemistry can go far in helping us. It cannot solve all of our problems, but I think it would be a big step forward. Thank you very much.
Thank you very much, Carol. I really appreciate your willingness to talk with us, for us and with us, and I'm sure that the audience will be really interested in some of the aspects that you brought up in your presentation. So I want to encourage the audience again to type the questions in as we are moving forward, and I will try to select some of those questions for the panel discussion, if not all of them. And right now I am ready to introduce our next speaker, Dr. Pamela Spencer, which is the Associate Director of the Toxicology and Environmental Research and Consulting branch of Dow Chemical in Saginaw, Michigan. Pam is actually one of our connection, the Grand Valley connection at the Dow, and we appreciate her willingness to talk with us today, especially that squeezing us in her busy program this afternoon. So Pam is going to present here the toxicology with an industrial point of view. So the floor is yours, Pam.
Thanks very much, and I'm glad I could join. Thank you for having me. I apologize I got your request for the slides as I was getting on the plane today, so I don't know if you got the actual PowerPoint slides or not, but I did send them when I got in. So so we'll go ahead and get started. Are these the PDF version that I'm looking at?
Yes, I think they are the PDF, yes.
Okay, all right. They may look a little different then, but that's okay. We'll go through it. So great. Well, I think I didn't hear the first presentation, and I'm really sorry I missed that, but it sounds like both previous speakers have just done a wonderful job of preparing the stage for what I want to talk about next, which is really talking about why I believe chemistry and toxicology and having chemists understand a little bit about toxicology is so important. And I call this why good products fail when chemistry and toxicology collide, because oftentimes as we're looking at new product development, the two can be in conflict, and that's where we can get into issues with viability of our products on the marketplace. So if we can go to the next slide. What I want to just cover just briefly is a little bit about the market trends, and you've heard some of this already, I think, with Carol's great presentation previously. Then talk a little bit about some of the challenges and opportunities that we see with regard to product development, what toxicology's role is, because that does play a very integral role oftentimes in the success of the products, and then how do we minimize those conflicts, and then some considerations for the future. So if we can go to the next slide. And as was pointed out, there is still concern growing over the safety of products in the marketplace, and we see this every day in the newspapers and in the headlines, and these just highlight a few of some of the more contemporary issues that we've been facing, and probably most well known, the little rubber ducky on the left there with the ban of BPA, bisphenol A, in children's toys. And so this continues to be a very significant public health concern for many reasons. If we go to the next slide. And the consequences of this public concern is that whether safety is real or perceived, it really doesn't matter. Even if it's perceived, the product is typically doomed for failure, and that means replacement. For us, perception is the reality. So it's really important to think about how can we anticipate potential safety concerns early so that we can improve the successful introduction of safer products. And what that really means is that we need to think about how we do screening in very, very early stages of our product development. So we'll go to the next slide. So let's talk a little bit about chemical design, and I'm going to use the guidepost here and talk about the past, the present, and where we need to go for the future. So next slide, please. All right, and in the past, I think Carol did a good job of giving the historical perspective there, but from a chemical design perspective, what we really focused on is the function of whatever we were developing, the performance, and the cost. And rarely in industrial chemicals do we have a situation where we were assessing for hazards up front. And as a result, as Carol pointed out, many substances were on the market that didn't have maybe all of the hazard information that they should have had. Next slide. And the consequences of this is that there were numerous public health and environmental issues that were then associated with chemical exposure. And this did a lot to really tarnish the industry's reputation, and it created a lack of trust and credibility, both with the public and the industry. So the next slide. And as a result of that, what we see today is that we've now have significant chemicals legislation globally. You can think about the registrations that we have under TSCA or the Office of Pesticide Program Office, REACH in the EU. But we've also seen the emergence of green chemistry, and as we've seen this, sustainability seems to be gaining a lot more importance for consumers as well as for industry that are putting together their sustainability goals. And if you look today, we have more than 300 now eco-labeling schemes and alternative assessment programs that are in place to help us identify and to promote materials that are safer and considered more environmentally friendly. And as was pointed out, the focus has been on reducing hazards as much as possible. And in some cases, the focus has been so much on reducing hazards that functionality can be compromised in favor of the hazard profile. So then we start to see that we are putting materials on the market that maybe don't function as effectively as what was previously used. So the next slide. And so this really creates a challenge for chemists and for scientists involved in product development. And if you look at this little schematic here, what you can think of is that we have a product that works well and it has some high hazard profiles. And what they really want us to do is to develop a product that's on the bottom right, where it's a low hazard, but it still looks and it still acts like the lion. But oftentimes what we find that we're getting is something that's far falls short of what the lion is that we really want. And so it's very much of a challenge for us to figure out how do we reduce hazard and keep the functionality and keep the cost and keep all of the other elements that are important in that product the same or better. Let's go to the next slide. So when you look at the future from an industry perspective, what we're looking at is how can we minimize hazards where possible without compromising function. And that really means understanding what makes something hazardous or toxic and deciding how we can design around it. And that comes very early on in the product development process. And this is why understanding toxicology and the impacts of that are so important from a design standpoint. Recognizing, though, hazard is really only part of the sustainable chemistry equation. Because avoiding hazards is not always going to be the most sustainable option. And if we look at things like solvents and painting cars or using preservatives in our materials to increase shelf life, there are certain things that we're going to have to accept are going to need to have a certain hazard profile in order to do their job, and they're going to have to be managed, and we're going to have to use that exposure versus plus hazard equals risk equation. So recognizing that risk is more important than hazard alone, and that some hazards are going to be necessary and they're going to have to be managed. So recognizing that and trying to balance all of that is really where the potential opportunities are for industry to work on developing more sustainable products. We'll go to the next slide. And we talked about this in the last presentation that a lot has come out with green chemistry and green engineering, and this is really the design of products and processes that minimize the use and generation of hazardous substances. So that means safer processes, safer products, and safe use of our products. And that's where toxicology really comes in and why it's important to have an understanding, at least a basic understanding of what the implications of that can mean for a product success as we're developing a new product. So let's go to the next slide. So in that context, and this will probably be a repeat of what you've already had, but then the science of toxicology is really devoted to the study of poison, and what we're talking about in modern terms is how can we define the limits of safety of that chemical substance, and that can be, you know, man-made or natural, as well as anything in between. So next slide. So when we think about general concepts, what we want our chemists to be thinking about is that toxicity is an intrinsic property of the chemical, and that it really implies that there's an adverse effect, which is a harmful or undesired effect. And also to understand that hazard comes in different types. There can be toxic, physical, chemical, and that these hazards not only have safety implications, but they have labeling and classification implications that can dictate how we can sell or transport our product, or the kinds of warnings that we have to have on our product. So that's also important to understand. And then to recognize as well that there's a safe dose, then that would be the highest level of exposure to a substance that would be considered not likely to produce an adverse effect in the population that we're looking at. And then the combination of risk, that hazard plus exposure equals risk. Because just because we identify a hazard early on doesn't mean that it's going to be the death of a product, I'll say. So we need to constantly keep in mind we're trying to do hazard identification, but we still have to do this in a risk context. Next slide. So with that, we have to be able to design and perform toxicity tests in order to characterize that toxicity of our chemicals so that we can understand what hazards are associated with it, define those safe levels, and assess the risks of handling and using that both for human health and the environment, and then provide the support that's needed once we've determined that we have a viable product that we want to take to market to support the regulatory submissions, any voluntary initiatives that we might want to have, as well as product advocacy or defense. And by voluntary initiatives, there might be, let's say, opportunities that we're trying to pursue a particular green label or marketing claim. And it's good to be aware of that so that you can recognize that up front as you're developing a new product. Next slide. So why are we doing this? I mean, we do want to do to reduce the hazards in our product, but we really want to promote the safe use of our chemicals and products. And so we want to do this as a company because it's good product stewardship. We want to understand how it can be used safely. We want to understand if there's any requirements for protective equipment. And we're also committed to these global product stewardship goals through the International Chemical Company Association, or Council of Chemicals. And we are required to ensure regulatory compliance. So we also have to make sure that we're meeting the regulations for whatever geographies we're going to want to sell this in, and that this is done prior to marketing, or in some cases as we're getting ready to enter the market. So it's important from a product stewardship standpoint and from a regulation standpoint to really understand the toxicology and the hazards of your material. Next slide. So why is this important from an industry standpoint is that any new product or existing product has to be tested, and it has to comply with global regulations. And not only is the compliance important, but it takes time and money to do this. So every time we register a new substance, and if we're looking, let's say, at a cost to register a smaller volume substance, it can cost as much as $500,000 and take 15 to 18 months of testing and time to prepare the registration that we want to submit. We might identify a hazard that's not compatible with the desired use, and that's important to us. Let's say if we identify a material that's an allergen, we're not going to want to use that material in cosmetics, or it could have implications that could be adverse for a product that's already on the market as well. Early involvement of the toxicologist is always desirable because it's going to help steer away from those unwanted hazards. And a basic understanding of toxicology with an R&D chemist or a person that's in product development will help that person recognize when they're developing new products, when they need to engage the experts, and when they might be able to make some decisions on their own to help avoid developing a product that would have a hazard that would be undesired in the marketplace. So let's go to the next slide. Now, historically, toxicology is not designed for R&D, and the reason that this is, and this was a build slide, so you'll have to kind of see through the busyness as we look on the PDF, but if you look at the way product development occurs in an industry platform, there's a design, a selection, and then there's the development stage, and typically the development stage is where the safety assessment occurs, and in the traditional toxicology testing paradigm, we're using studies with animals, usually lots of animals that cost lots of money and take lots of time the later we get into the development process and the development phase. Because as we're getting ready to market a product, we're also getting ready to register it. So the question is, how can we move the considerations of hazards earlier into the product development process? And that's really important from a green chemistry standpoint, and just in general from improving our product stewardship. So if we go to the next slide, What we know about R&D is that they need to have some awareness about toxicology and how it's associated with design choices, in that they have to be thinking about human and environmental health endpoints. We're not just talking about function and performance anymore. And what they need to understand what kind of data is useful that can help inform molecular design, inform wise decisions, and inform the regulatory safety assessment procedures. So how do we tailor that testing? But more importantly, it has to be rapid and it has to be relatively inexpensive. And we have to be able to do these assessments with small amounts of test material, because in the early R&D phase, we don't have much test material, or sometimes we have no test material, and we're just looking at structures on a piece of paper that maybe the chemist is considering at that point. So the next slide. And these are just some examples of how you could train chemists to start to recognize known toxicophores, and to have some idea that, geez, if I see this general structure in a material that I'm trying to develop, I might want to, do a little bit further investigation to make sure that I'm not posing an opportunity to introduce some toxic effects or known effects that are associated also with those toxicophores. Next slide. And then this goes on because there's many other structural moieties that are associated with toxicity, epoxides, hydrazines, all of the things that you see on the slide there. So just simply having an understanding of the fact that there's certain structural moieties that they may choose because they have a really desired function might also carry with it an associated toxicity, and having that understanding can help them be aware and to do the proper evaluation early. Next slide. So when you look at the R&D process, this is really an iterative nature when you're looking at it in an industrial setting. I mean, we're looking at molecular design and synthesis. We look at performance and efficacy. We look at mammalian toxicity and ecotox, environmental fate. And all of this is going on in conjunction with our R&D teams. And so from a training standpoint, it's important that all professionals that are engaged in product development have some understanding of what each other is doing, and to cultivate that collaborative working environment. And toxicologists need to be able to communicate with a diverse body of experts, and chemists need to be able to communicate with the toxicologists and have that awareness as we're going through the product development phase. Next slide. So if you look at how we can integrate toxicology early into project management, certainly having the chemist understand that toxicity is an important part from the very early stages, we can start to incorporate some early evaluations according to what we call our stage gate design. And the stage gate process is a very well-defined process that's used frequently in industry, and it's really intended to ask certain questions at each gate, and to ask those questions and to pass those questions before you decide that you can go to the next level of product development. So there's an ideation stage, concept shaping, concept analysis, all the way through development and realization. And the idea here is that when you're working in an R&D setting, you'd really like to do what we call front-end loading, which is generate as much knowledge as early as possible while you still have options open to go to another maybe design project. So we want to fail fast and succeed early. So we look at this as two phases of R&D. Early, we want to quickly eliminate poor candidates and absorb whatever risks. We recognize that we might be using tools that could be overly conservative and cause us to eliminate good candidates early. But late, what it's going to do is increase the probability of a successful launch, and that will have an alternate candidate with equal performance, acceptable toxicity, and environmental profiles, and equivalent economics. So that's the whole idea behind introducing these assessments early in product development. Next slide. And this is just a schematic of how this can be done and some of the types of screening tools that can be used at the various phases. So if you look at early on where we're talking about very small amounts of test material or maybe no test material at all, we can conduct literature searches, look at physical chemical properties, but try to flag issues early for testing. And then as we continue to go into the development stage, we're doing some in vitro or in silico type of testing, ultimately getting into a little bit more of traditional acute testing. And by going through that front-end loading in the research, we can then pay huge dividends in the development side, because as we get to these more expensive studies that we're going to be doing for our product safety assessments and registration, we're going to make sure we have the best products that we're advancing forward, and we're going to be saving money. It's going to be less waste. Next slide. And I want to just give you one example, I guess I'll call it a case study, of how we were effectively able to do this and working with chemists who understood some of the adverse impacts that were happening with the material. And here's a fungicide that's been on the market for some time in Europe. It's called Curethane, and it's used on vineyards in Europe. And there was teratogenic effects associated in rodents, and this was in the form of palate and torticollis, which is the head tilt where it causes the animal to have a circling behavior in the swim test. And the no observable effect level was 4 milligrams per kilogram in mice. And we believe that this torticollis was caused by an oticonial agenesis. And the oticonia, it's a little hard to see in this picture, but they really contain crystals of calcium carbonate or ear dust, and that's what helps give the balance. And so there was an effort to phase out this product and to search for a less hazardous substitute because of this teratogenic effect. We go to the next slide. And this just shows you a control and a Dynacap exposed animal, and you can see where the yellow arrows are, little curlicue structures. Those are the normal oticonia, and you can see that in the treated animals they're absent. Next slide. So the hypothesis was there were 6 isomers in Dynacap, and there was some early evidence that suggested perhaps 2 isomers were not teratogenic. So working with the R&D chemists, they were able to discover a method to do a large-scale synthesis of the isomers. And then in developing a mouse teratogenesis screen, we were able to test each one of these isomers individually and then select the isomer that did not exhibit the teratogenic effect and have that move in as the lead candidate for substitution. So it was the 6 MH isomer, and when we tested this, there was no developmental toxicity. And not only was there not any developmental toxicity, but if you look at the no observable effect level for just the general toxicity, it was much higher than the isomeric mixture. So we went on to do further testing. It also was not developmentally toxic in rats or rabbits. And it was also, it exhibited the same fungicidal efficacy. And so through this work, what it did is really result in commercialization of a product that was just as efficacious but did not have the teratogenic effects. And so we had a non-teratogenic replacement for the fungicide. Next slide, please. So that's a success story, and as we're doing that, I like to bring people back to remember that as we're making substitutions and as we're looking at hazards that we're trying to design out, we still have to keep in mind that we need to be ever cognizant of the opportunity for unintended consequences of a replacement. And when I say unintended consequences, what I mean is that we really need to be thinking of a life cycle-like mindset, and this is where the sustainability aspect comes in. And that means that even though we've engineered out a certain hazard from a material or designed it out, we still need to confirm that the substitute does not have greater or unknown toxicity or exposure potential in another area of the value chain. And that means that we're not transferring risk, say, from a consumer use maybe to a manufacturing use now, and we're putting our workers at greater risk because of some change in process. So that does all have to be balanced as we're looking across substitution. Next slide. I just want to point out as we get to the last few slides how important it is to get it right the first time, that getting it right the first time can pay huge dividends. A case in point is if we look at an agricultural product, the development of those products, this is probably what I would consider the most labor-intensive and resource-intensive type of product to develop. It can take 10 years and $250 million of research, development, and preparation to register the new crop protection product. These are really tightly regulated products. There's only 1 in 139,000 chemicals that we evaluate that successfully progress from the lab to the field. And a product for this particular product type undergoes more than 100 regulatory studies to support the health and safety and environmental assessments that are required for registration. So you can imagine the lost time and resources and effort if we get a product too far down the developmental stage before we realize that it's not going to be a viable alternative. So having chemists that understand this early and can help engage the right expertise to assess these up front has a tremendous value for industry. Next slide. So with that, I just want to conclude with the fact that, you know, we are continuing to see increased concerns over product safety, and that these do impact the success and the life of a product on the marketplace, whether they're real or not. That regulatory suppliers and consumers are, you know, their demands can be important showstoppers in the development of a new product. If they decide they don't want a certain, you know, a classification, or there's certain regulatory restrictions, or they create ban lists, that's all going to result in consumer deselection. So it's important to understand and to be assessing for that up front. And the best way to do that is with having trained professionals that are involved in the product development and formulation of new products, and professionals who really understand the basic principles of toxicology, because that's going to help us identify the issues early, advance the safest products to market quicker, and save time, resources, and money. So with that, I'll just conclude and thank you, and take any questions if there's any.
Thank you very much, Pam. That was a very interesting presentation and certainly a totally different point of view. And with this in mind, we closed the 3 presentations, and I'm inviting our three speakers, to whom I'm very thankful at this point again, to be ready for a panel discussion. And the audience, I know it may be overwhelming because there is a lot of information here, but please be patient and help us with your questions so we can direct the conversation. What I would like to do in the short time that is left here is to bring your attention again to the fact that our purpose is to define the need for toxicology in the making of a chemist. And we put the green chemist there because we see the connection between the green chemistry and toxicology. And before I turn the microphone to the panelists, I want to say that if we are not going to be able to go over all the questions and answer to all the issues that are going to be raised or are raised here, we are inviting everybody on the forum that is going to be open on Michigan Green Chemistry Clearinghouse and continue this conversation. And I hope that our panelists will be willing to continue to log in and answer to questions and keep the conversation going. I would like to believe that Carol made a very nice introduction to green chemistry, putting the definition of green chemistry up there and mentioning that it's the design of chemical product processes, and immediately make the connection with the risk as a function of hazard and exposure, and how green chemistry can bring the hazard down, not only the exposure, in order to reduce the risk. So my question for our panelists here is, what do we think will be beneficial for a chemist in his training, in his basic training? What are the things that he should be aware of? What are the things that he should know, and which are the things or the subject or the issues that he should be proficient in order to become a good and productive green chemist? I will extend maybe the question in order to the idea to be hired, to secure a job, to be successful in an R&D setting, and so on and so forth. By listening to all of you, I realize that there is the complexity issue arises from all of your presentation. The environmental toxicology is overwhelming considering how many areas it covers. The toxicity tests and the complexity of assessing toxicity is also overwhelming. And then the problem that Pam brought up about how can we balance the efficacy with harm or toxicity. So I think the conversation is just ready to begin by even at the closing of this seminar. So I would like you to try to maybe answer one at a time. I know we are in different places and we have access to, I hope that Clinton can put you online. So let's see what would be beneficial for a chemist to learn in terms of toxicology, and what would be, let's say, a basic level of toxicology, what they should know, and when the proficiency in some direction will be necessary in their preparation. So I turn the microphone to you, and if you want to go in or the order that you presented will be fine. So this will mean Rick, Carol, and then Pam, or if you want to switch and somebody else wants to start, that will be fine.
I can go first. Am I on here?
Yes.
Okay. I think probably looking for just a basic awareness of toxicology, the principles, and some historical examples. But I think we're looking for a chemist in the industrial setting to have some sensitivity to that. In addition to be sensitive about getting good % yields and the types of things that you're concerned about with respect to product performance or product production, I think it's very important to just have that sensitivity or that awareness that there are toxicology and safety principles that you have to consider in addition to that. And if you have some knowledge of those fundamentals, then you can look that information up when you're talking about a new product or something like that, or you can have that in your back of your mind when you're developing synthesis routes, asking those questions, or maybe not find the answer yourself, but being aware that that could be an issue, and then going to the right person in the company or in the academia for that information. So I think it's just having that basic sense of awareness and some background, what to know, what the right questions to ask are, and where to get that information, I think is very important.
Okay, thank you, Rick. Somebody else?
Yeah, Rick, I think that's a good answer. I mean, I think that the challenge is that you're not trying to take chemists and turn them into toxicologists.
Correct.
And so I think there is a balance, but I think this awareness issue is really an important one. I think that actually, the green chemistry, while reducing hazards, has many other facets to it in terms of being sustainable, as being a part of sustainability, reducing waste, saving energy, those kinds of issues. So I think understanding the principles would go far. And then, you were really talking about maybe a toxicology light course to sort of hit the principles, hit the high spots, so that there is an awareness of the science of toxicology. It's rapidly changing, so trying to keep up with it is going to be kind of a challenge. But I also agree with Rick to actually understand that maybe there are questions that have to be asked. I would say that there are some software programs that are being developed that help bench chemists make choices like this. I'm not sure exactly what the status is, but there have been several companies that have been trying to do that. So I think there might be a variety of approaches that could be used to try and achieve this goal of increasing awareness.
Yeah, that's a great idea, Pam.
Yeah, I would agree. I mean, we definitely do not want to create toxicologists out of chemists, and I do think awareness is important, and awareness in understanding what the implications are if you have a hazard, and and that means not just understanding the concepts of toxicology, but how does that translate into what happens to that product later in classifications. If you've got a classification as a carcinogen, it's done. Chemists need to understand that. And Carol, to your point, tools, I mean, there are a number of tools that are out there now that do at least go through and can either give you structural alerts for those kinds of things, or can tell you if they are on lists already that would have classifications that would say this is probably a hazard that we're not going to want to continue to develop the product because of that classification. And I know the Works is one that has a search engine like that you can go through and look. I think there's a couple of other, like DSS Tox, I think also through the EPA can do that. So I think having that general understanding, knowing what tools are at their, available for their use, and then knowing when you probably should ask to seek the advice of an expert is important.
Okay, thank you so very much. It looks like the time is flying here when we are talking about things that we are very interested in. I would like you to notice the forum address that we are going to have it open for questions, and we would really appreciate if you will be kind enough to answer to the questions that will be posted on the forum. And we hope that this conversation would lead to better results, at least for our little part of the world, if not for what ACS really requires from our graduates. Because I have to go back at the slide that very nicely Carol put it up, in which she indicates what ACS requires. And the only word that goes there is safety. And it's safety. It's very good, but we think that we may go a little bit farther there to bring the awareness about toxicity. And as you mentioned, have the basic concepts, have the tools, and maybe know how to utilize them, and then know when to seek the help of an expert. Unfortunately, we have to close here because we are already past the time that we were supposed to end our webinar today. Thank you very much, everybody, for participation, and thank you for your time and your willingness to talk for us. And we hope to continue our collaboration, and we will take the liberty to contact you if we need more help with answering to the questions on the forum. Thank you, everybody, again.
Thank you.
Thank you.